starts. And it's, again, there's also some envy. So in the standard machine learning world, like, let's assume you do diagnostics with machine learning and you want to do cancer prediction. So this is cool. If you reach 90% performance and with 90% you predict cancer or non-cancer, you are really good. You did a huge contribution to the world. Now, if this humanoid robot, every 10th time it comes up on the stage, falls over, that would be 90% success rate. You wouldn't look at it, okay? You wouldn't like it. You would throw it away. So what is the message behind this? Really, the physical world is very, very strict with performance. And things which work in other machine learning domains are not really acceptable in the physical world. And this is then the question, how do you get to this high level of performance? So where can we apply AI-enabled robotics? And there's many ways how you can get started. So this is more the industrial world at the beginning. This is more unstructured environments on the right side. I think from our vision in where I am working, we start much more on the structured and semi-structured side, because this is where we can actually get robots out which can really do something and which people will find useful, while the less structured environments are just much harder to get into. They're also, if you're a startup company, they're just commercially less viable because you will take a long time before you get any revenue, and at some point you have to make some investors happy to actually keep on funding what you're doing. So this is also, so we are currently preferring actually in our work much more this kind of industrial side of things with semi-structure rather going into too unstructured environments. Despite this is super valuable if you can do this, obviously. This is just, I think in industry people call about something like the go-to-market strategy and product market fit. Weird words. This is us just telling you how can you be successful without getting bankrupt. What's happening in the world of robotics? I think there's obviously a couple of things which happened. Artificial intelligence, big data has made huge progress, particularly in the last 2 or 3 years. I think everybody will agree on this, the typical transformer model. And this is partially the reason that everybody is sitting here, because this has become such a hot topic where everybody hopes that robotics can also make a huge jump forward. Now, the big jumps have been in large language models, in so language processing, in vision processing. Robotics has been pretty reluctant to make a transformative step forward. You see a lot of progress and lots of cool things, but there's nothing like a step where suddenly things get really, really much better in an unexpected, I think people call it the GPT event these days. This hasn't happened yet, and it's questionable whether physics will comply with your wishes at some point. So to be seen. Now, other good things are, of course, happening. We have way more computing in the world, whether it's GPUs or TPUs. We have novel sensors which can see things which could not be seen before. So these are some special cameras which work with polarized light, and they can actually see transparent and shiny objects without any trouble and really help you to have vision which is not impoverished. And then in the middle comes something which is really important. I think you need to get algorithms, data, and software infrastructure together. And I think there's increasingly more robotics platforms where you can do this. I think the most famous one is clearly ROS. And I think at Instrinsic and Google, we're working on something similar on a much more professional and larger base. But these things coming together, in particular, if you can get the software infrastructure to accelerate between sensing and artificial intelligence computing, that would be really fantastic. And I think they're not quite there yet. Everybody's working on their own thing, to be honest. And everybody is reinventing robotics for the, I don't know, 10,000th time, most likely. So, how to get to more intelligent AI robots? And there's obviously the big vision, AGI, Artificial General Intelligence, which is in everybody's mouth now. We're actually even talking about superhuman intelligence these days, but I think the robots are not even close to that. So AGI, what is kind of the characteristics? End-to-end learning. So you want to learn the entire thing. You want to learn large generalist models, and you focus on a really general system. That means you prefer generalization, and currently at least people sacrifice performance a fair amount. And this is clearly what we should be doing, and this is super exciting. But it's also potentially a very long path to get there, to be honest, particularly to get there such that it is useful in practical applications. From a pure research point of view, if you're just focusing on research, there's no doubt about that this is the coolest thing you can work on. Now let's make this a little bit more boring, but more down to earth. So let's say you don't want, well, you cannot wait to get to the big AGI event, and you still want to survive and do something with your robots with AI on machine learning. So why not do something which is called artificial specialized intelligence? And there's other words for that as well. So many people have been using this before. And that is much more, as you see now, much more down to earth. So these are what many people might have seen before. These are the NIST, National Institute of Standards and Technology in the United States. There's a challenge board about some electronics manufacturing. So this is a relatively small domain. It's about connector insertion and screwing and putting bolts on things and whatsoever. But why not have a robot being able to do just this domain, but do it really, really well? And I find connector insertion is kind of a cool thing. Okay, we made it up. It is completely artificial. We created connector insertion, putting a connector into a socket, and a little child can learn how to do this by the age of 2 or 3, and it's not very complicated anymore. And still with robots, we have actually a huge problem to do this in general, because these parts are inaccurate, you have to perceive them, you make errors in perception, then you have to basically control, and that has to be correct. And it's surprisingly, nobody has done this little NIST board, which has been out as a challenge for 3-4 years. Nobody has done this in its complexity, where all the parts come randomly in a bin, and then you have to put them on there, and you should do this fast and reliably, and then take them apart afterwards again. So this kind of ASI view is really about much smaller models, which are machine learning, reinforcement learning, foundation models. But the hope is that they are high performance in a narrow domain. And silly things, they also run on-premise. What does that mean? That means they run locally on your computer. So it turns out industry is not super interested in cloud computing all the time. They don't like the cloud. They partially don't even like to connect to the cloud because they're worried they'll lose some private data and other things. And there's also this other component that people talk industry about air-gapped computing. What happens if the internet to the external world does not work? You cannot afford that your entire factory stands still because of that. So that means lots of things have to run locally on-premise in the particular factory, and it has to run reliably, which often means it cannot be the biggest models in the world. So a little bit of a comparison. So this vision of artificial specialized intelligence has just more focused models, has special models for perception, for planning, for grasping, for instance, for task planning, for single robot motion planning, multiple robot motion planning, contact manipulation, short-term horizon planning. It is just much more focused with many machine learning models rather than, in contrast, the very big generalist model, which does everything together. Interaction, perception, control, language, whatever you need. I have interaction twice, interesting. Then sensory inputs are directly mapped to the robot. You do long horizon end-to-end performance, and there's lots of models which have been trying to show that. Let me see, what are the pros and cons if you go into this? Well, the specialized models obviously get you special models for everything. It supports what is called multi-rate systems, and I will get to this in the next slide. It means controlling robotics happens on different frequencies, on different timescales, and you have to take this into account. But they are also efficient now, and to run, they're small sizes, they can run in real time. Okay, I go nuts when I see people shooting robot commands at 1 hertz at a robot, or 5 hertz. Control starts at 500 hertz, a kilohertz, or whatsoever. So real-time control in proper robotics is not done on a very, very slow time scale. What's nice about these models then is also they can be debugged more easily and you can better understand them and run them on premise. Of course, they are not as flexible, they're not as cool, and they will not solve AGI just like that. And in contrast, then, if you look at AGI models, they're obviously much bigger, they can do much more, but they are much harder to deploy actually in real-time robotics on-premise, and they're really big, so they don't compute the way we want them to compute in robotics many times. So let me get to this multi-rate system, which is actually a really important component. So robotics just happens on multiple timescales. And your human body works on multiple timescales as well. You have certain processing which just go through your spinal cord, certain things which go through a lower part of your brain, and certain things which go long-term over a long circle to the frontal part of your brain. So all animals are actually built like this. They work on multiple timescales. And certain things like reasoning and planning, motion and task planning, you can take more time. When it comes to really processing sensory systems and go to the real control, you want to be on a really high time scale. So I have one fun component in life, like sensory processing. I've had some discussions with colleagues when I told them, oh, why don't you use touch perception and kind of force torque sensing in your learning models? And they then put it in and said, no, it doesn't help at all. Yeah, so at which frequency did you control? Oh yeah, we controlled at 10 hertz. Now it turns out force torque events, touch events, happen on the scale of a couple of milliseconds. If you, and force torque sensors usually run at a kilohertz or something like that. That means if you sample data with 10 hertz from a 1 kilohertz running force torque sensor, you're missing 99% of the data. It's completely terrible. So you need to think, again, coming back to my favorite message, you need to think about the physics of what's happening out there. And if you don't think about this, you will potentially miss and not have the right data to work with. And I really like a slide from Jonathan Hurst. So Jonathan Hurst is from Agility Robotics, and he has that slide. Agility Robotics is one of the kind of humanoid robotics companies. They have the Digit robot, as it's called. And this is a slide which I just stole from one of his presentations. And it's literally the same slide what I showed you before. This is basically looking at the different frequencies at which a robot is running, where at the high control rate, you don't need a lot of information or AI information. And just later on, if you come to planning, coordination, cognition, you need much more data and you need to use different models. And he actually really nicely listed what is kind of suitable at which time scale, which is the same message that we've been having for a while. It's just independently that he showed these things, which is cool. It's a really good slide. So now, I fully would love to create physical AGI. And I think this is what everybody's here about and what we would like to accomplish. And the question is essentially how to get there. And this is, I've actually been borrowing some of the terminology from Karl Hausmann from Physical Intelligence. And he nicely said that you can span at least one particular space in this domain of physical AGI by looking at how much performance do you get, then how much generalization do you get, and what are the cool things you can do with it? It means what they call capabilities. That means how many complicated tasks can you do? Can you only just do relatively simple and boring tasks, or can you do really complicated tasks, like t-shirt folding and things which are beyond the domain which has normally been done in robotics? And I put this AGI up here, and I put this artificial specialized intelligence down there, which is high up on the performance scale, but not so high up on the capability scales and the generalization scale. And now you can basically say, taking this plot, you can basically argue a little bit how to get to physical artificial intelligence. And so the way we've been taking in our approach is really we need performance first. This really matters for us because otherwise we cannot work with anybody who would like to deploy our robots and have fun with that, and they say, hey, they're actually useful. And so if you go first in this direction, yes, you will not be as general. This is like the SNIS taskboard which I showed you. You will not have the coolest capabilities of what you can do, but you actually do something and the robots work and people will use them. And then you can try to iterate higher up towards this AGI scale. But on the way, you actually have robots which are working and which create data. And then hopefully you can actually get all this data and use that to get higher up in this path. So this is one vision. It's not what everybody will agree on, and I think people will discuss that. Thank you. So here are some other paths how to get there. And this is actually, Physical Intelligence had a little blog post or podcast recently, and they really described that they used a very different way to get there. They said initially they wanted to show capabilities, new capabilities that robots couldn't be doing before. Then they wanted to go into the direction of generalization. And I think currently their main goal is like, how do we get to performance? Performance is miserable, and its performance is really, I think, one of the holy grails which we have to take. And whatever you see, whenever you see AI, machine learning approaches to robotics, look at the numbers where they get. And sorry, 60, 70%, 80%, this is not enough. It needs to get better. Now, of course, you can ignore all these strategies and just collect data like crazy and hope there's a direct path to AGI. This is also a reasonable thing to do. And none of us knows what's really the right way and what is the most successful way, and whether the robots will play along with the one way or the other way. Everybody has to decide this by themselves in the context of what you try to accomplish. But it's kind of fun to look at this in this context. Data. I think we've been hearing about data in the first presentations already. Now, where is the data for robotics? Well, this is a nice little plot which shows, fine, there's internet scale of data. Then there's, and that's a lot, okay? There's the entire internet. This is what you use for large language models. Then there's simulation data. NVIDIA is fantastic in doing simulation data. And because you can simulate in the cloud, you can still create a lot of data. Now, we are betting a little bit more on data from kind of artificial specialized intelligence, robotic work cells, which basically will be deployed at least and create data over time. And then there's, of course, data which we can get from human teleoperations, which is a painfully slow job, and it's very hard to create data at scale. Now, all of this data, so from the viewpoint where we come from, is actually has to sit on a decent robotics platform. On a robotics platform, reiterating what I said before, has real-time control, which is done correct. It has as much as possible of perception that we already know. So one thing, please, let's not throw away all the knowledge that people have been doing in robotics and in perception, computer vision, and whatsoever in the past. Use it. Use it as much as possible, and only add machine learning where you need. And then comes machine learning, and then multi-robot coordination, yet very boring thing, safety. Without safety, you will not get a robot out in the world. They will basically not allow you, or you have to be in a cage. This plot is a little bit misleading, since the real distribution of the data looks, well, it's my minimal PowerPoint artistry, how the data distribution looks like. To be honest, this will just be a tiny, tiny needle relative to this huge amount of data which is on the internet. How many robots are out in the world? On the order of 10 million, maybe 15 million. I think Tesla has more cars out there, by far. So we actually have very, very little data, and we will not be able to create a huge amount of data that easily with that small number of robots we have. And then you can also ask the question, now, if you wait for the GPT event in this world, do we have enough data? Can we train? Do we have the right models? If the models are as hungry as the normal transformer architectures, maybe this is the wrong approach. Maybe we will never have enough data from robots. And it's a huge question mark. I don't know the answer, but it's at least a question it's worthwhile asking. So, fine. What we are betting on is this kind of generic robotics platform, which we would use for any form of AI-enabled robotics, built on whatever technology that is already available. And just to give you a tiny vision about how we would be thinking about this, we use as much of knowledge as we have in terms of control, perception, and then arm farms, which create data as much as possible automatically. No, it's 50 seconds still left. And so one little vision which we have, and it's a vision video, and this is not all realistic what you see on that here. But this is how we would envision at some point that you interact with an intelligent robot in its kind of software system, that you provide sketches, you provide photos, you have all kinds of VLMs at least which help you in doing this. A user basically interacts with it, but then the system also automatically creates code. It does not do everything end to end. It uses state machines, for instance, which are easily created in code, and then basically see how far these things, this is the traditional approach to robotics, see how far this goes and what it can do. And if it does not work well enough, well, then maybe you have to add something which is more intelligent. You have to potentially add a reinforcement learning skills. And actually what you're going to see right now, the reinforcement learning is from Jinlan Lu actually, so this is part of his work. And you can start teaching a robot what it's supposed to do, then it will go to automatic training afterwards. So, almost done. So you will see some training happening afterwards. So this is now the robot starts to train autonomously, doesn't need demonstrations anymore. And after actually the beautiful work of Jinlan, with about 20 to 30 minutes of training, the system becomes actually more than 99% performance correct. So then you can deploy this. Now suddenly you have a machine learning skill in a traditional robotics workflow, but this is kind of the ASI view. This is kind of more down to earth, and this might actually work, and we believe that can actually be done. So this is not so far away. We did this video actually 1.5 years ago, and I think everybody would agree this is not so far away from realizing that. And as a last component, it actually starts to work. So this is just a little bit of videos put together which show the entire workflow, and it's going to be fine enough. So let me end at this point. So this is a more conservative view of how to use AI-enabled robotics. It really says end-to-end learning, maybe I don't need this. Maybe I do end-to-end by calling actually functions which are skills in a more standardized robotics workflow when I only insert machine learning at the moments where I need it. At least this will get us to something which works in the real world, but it's not as cool as AGI at this moment. But maybe it's the path to get there in a different way. Thank you very much.
Thank you. Thank you so much for your wonderful speech. Please take your seats. Thank you.